This is the second of two episodes in which we're thinking about multi-component solutions. And if you haven't watched the first part, I would encourage you to do so at the moment, because this will essentially follow on from that. So in that previous episode, we looked at making up a multi-component solution when it was phrased for us in the style presented on the screen here. So one sentence describing the solution that we wanted to make and the various bits that were going to fit into that. Now, this time we're going to think about a question that's got similar sorts of calculations to be done, but it has been presented to you in a slightly different way. So here we're seeing components listed for us in a table. This is the components in this particular example, the one that we're going to work through for this video, is the components that would go into a polymerase chain reaction, a PCR reaction. Now, in reality, you'll be presented in a lab context, you'd be presented with a situation where we would know what the stock concentration was for each of our components, we would know what the final concentration we needed was, and we would be asked in all circumstances to be calculating the amount that we would need to make a stock solution. Now there's a sting in the tail there that I'll come back to in a moment. But essentially that would be the basic pattern of a question like this. But for purposes of teaching and learning, often you'll see a question like this presented to you in a slightly different way. So we might, for example, be given various components where we're told the answer, but we've got a scattering of different things to work out. So it might still sometimes be the volume that we need to add, but it might be sometimes working out what the stock concentration would be given some of the other components, or indeed to work out what the final concentration would be itself. Now, as I hinted, there is a trick or a catch in this, and I'm going to work that through in those slides, and I'm going to do so by presenting this with some numbers. So following through from the previous slide, I've kept the components that I need to calculate in the same positions in this particular case. The question, the components of a PCR buffer and the working concentrations for a PCR reaction are shown in the table below. PCR buffer is made at 10 times stock, which is then used at 1 times final concentration in the reaction mix. Complete the table by calculating the missing values, including appropriate units as necessary. Now, here's the catch, the thing that you must remember to notice here. PCR buffer is made as a 10 times stock, but will be used as a 1 times final concentration. And so the final column here, the right hand side column, is telling us the final concentrations that we need in the PCR reactions. What we're going to be asked to make, though, is our 10 times stock. So in some senses, this middle column is actually our final reaction of the initial calculations, but we need to factor in that the concentrations we need in that column need to be 10 times what we'll want in the final reactions, and that we're making those up from stock concentrations. And here, this left-hand column, stock concentration, is describing the stock of each of the individual components. So how does that look in practice? Well, let's begin by thinking about the amount that we would need of the various substances for this 10 times buffer. So if in the first case, for example, if our final concentration of the tris HCl needs to be 45 millimolar, for our 10 times stock, in our 10 times stock, we're going to need 450 millimolar. Similarly, for the ammonium sulfate, we're going to need 110 millimolar. Interestingly, for this calculation here and this calculation here, the number we haven't been told is the final concentration. So we're going to have to handle that slightly differently. We'll come back to that in a moment. For our 2-mercaptoethanol, the beta-mercaptoethanol, 0.5%. For the EDTA, 40 micromolar. For each of the different components, the DATP, DCTP, DGTP and DTTP, our stock, 10 times stock will be 10 millimolar. And as I say, the BSA will be slightly different overall. And then having worked out all those separate components, we will then need to work out how much water we need to add. So that's the slight catch here. We need to remember that the concentration that we're making needs to be 10 times higher than the ones that we will actually use in the reaction. So let's work those through over the next few slides. To begin with then, the tris HCl. The final concentration we were quoted as needing was 45 millimolar. So as we've already demonstrated, our 10 times stock that we're making, our 10 times PCR stock, will need 450 millimolar, or we could say that's 0.45 molar. As usual, I'm going to begin by writing down that the initial volume multiplied by the initial concentration is the final volume multiplied by the final concentration. In this case, the stock was 2 molar concentration. We know that for all these calculations we need to end up with 600 microliters. That's how much of our PCR mix that we're making up. And I've elected to take, from these possibilities, I've elected to describe the final concentration as 0.45 molar because that means the units are the same on both sides, and therefore my unknown is in microliters already. So I can calculate that. Our unknown number of microliters is 600 times 0.45 divided by 2, which gives us an answer of 135 microliters. So that's my first component that I've calculated ready for making up my solution. Secondly, the ammonium sulfate. The final concentration of that's going to be 11 millimolar. So whilst I'm making up a 10 times stock, I need to make that as though it was 110 millimolar. As always, my initial volume times my initial concentration is my final volume times the final concentration. What information do I have already? Well, I was told that we need 66 microliters. We're trying in this case to determine what the concentration is. We've got our final volume for all of these calculations is 600 microliters, and our final concentration that we need is 110 millimolar. Now the units for volume on both sides of the equation are the same, so I know that initially at least I can think about my concentration in terms of millimolar the same as it is on the right hand side. So my unknown in millimolar is 600 times 110 divided by 66, which gives me the answer of 1000 millimolar, and clearly we're not going to leave that in terms of 1000 millimolar. That is 1 molar. So our concentration of the stock of ammonium sulfate is a 1 molar stock solution. Now the third component, you'll remember, is the one which I said we'd have to handle slightly differently. And that's because you are initially calculating a 10 times PCR stock, and we're going to have to work back in the other direction to get to knowing what the final concentration is. And so having done our calculation this time, the concentration that we calculate will need to be divided by 10 in order to get to the final concentration that we're going to be stating. What does that mean in practice for the magnesium chloride here? So working that through then, I'll start by writing VI times CI equals VF times CF as usual. I put in the components that I know. So 27 microliters multiplied by 1 molar is 600 microliters multiplied by my unknown amount in terms of the concentration. Now I can state that this is in molar at the moment because these units matched up already, and so I know that my unknown is going to be in the units that I had on the left hand side. Having said that though, I have some alarm bells ringing here straight away because I can see that 27 times 1 on the left hand side here is very much smaller than 600 microliters on the other side. So I rather suspect, I have a sensible hunch that my answer is actually going to end up with a much smaller concentration than 1. And so perhaps unusually, I'm going to change the units on both sides to make that, prepare for that. So 27 microlitres multiplied by 1000 millimolar is 600 microlitres times my unknown now in millimolar. And so I can work through that calculation, and that will give me the answer of 45 millimolar. So far so good, but remember, we haven't finished yet, because our final concentration is going to be 1/10 of that. So in completing my table, I need to remember then that the final concentration is going to be 4.5 millimolar on this occasion, and not 45. Okay, so I've worked through those first 3 examples for you. Now is an opportunity for you to pause the video and to complete the rest of the information that's needed in this table. You've had all the examples you need in order to be able to do that. There are a variety of calculations in the rest of the table here, but all of them are exemplified by the 3 that we've gone through already. So I do encourage you to pause the video for a bit, work out the answers there, and then to use the rest of the video as a way of checking that your answers were correct. Okay, well, let's work through the rest of the components that we're going to go into our solution, remembering that at the end of the day we've still got to make it all together into one multi-component solution. Starting with the 2-mercaptoethanol, the final concentration was 0.05%, so if I'm making up my 10 times PCR stock, I know the concentration is going to be 0.5%. VI times CI equals VF times CF. I put in the components that I know. In this case, both concentrations have been quoted in percent, and so therefore I know that they're going to match, and so my units for volume are going to be microlitres, the same as they are on the right hand side. My unknown in microlitres is going to be 600 times 0.5 divided by 100, which is 3 microlitres. Next, the EDTA. And so the final concentration is 4 micromolar. That means my PCR stock is going to need to be 40 micromolar. VI times CI equals VF times CF. I put in the components that I know. So 2 microlitres, 600 microlitres, and 40 micromolar. Again, the volume units this time are the same on both the left and the right hand sides. So I know that my unknown is going to be in micromolar, and that's equal to 600 times 40 divided by 2, which is 12,000 micromolar. I clearly don't want to have that stated in that way. Next, the DATP, final concentration 1 millimolar. So the PCR stock will need to be 10 millimolar, 10 times as much. VI times CI equals VF times CF. My unknown is in microlitres because these units left and right are already the same, matching up. So my unknown number of microlitres is 600 times 10 divided by 100, which is 60 microlitres. That's my answer for DATP. Hopefully you spotted, without having to go through it 4 times, that in fact that's also the same, also true for the DCTP, the DGTP, and the DTTP. And that means we've only got one component left to work out. And as we saw previously for the magnesium chloride, this is back to front compared with the other ones. So given the information that we've been presented with, we are initially calculating the 10 times PCR stock. And so we need to remember that the final concentration is going to be 1/10 of that. As usual, VI times CI equals VF times CF. 66 microlitres at 10 mg per mil is going to be being made up to 600 microlitres at an unknown number of mgs per mil. So my unknown is 66 times 10 divided by 600, which is 1.1 mgs per mil. So far so good, but for our to make up our 10 times stock. So in terms of quoting the final concentration that we need, that's going to be 1/10 of that, which is 0.11 mgs per mil, or better stated is 110 micrograms per mil. So we've worked through our different components, but we haven't actually made up our solution yet. So here's that information added to our original table. We've now got then a complete list of volumes in the middle column here, and we know that our final volume we want is 600 microlitres. So in terms of how much water we're going to need, the amount of water that we need is going to be the rest of those components taken away from 600. So we've got 600 minus 135 plus 66 plus 27 plus 3 plus 2 plus 4 lots of 60 and one lot of... Add all of those together and then take them away, and that leaves us needing 61 microlitres of water. So I hope that what you can see here is, although the question looked quite complicated, actually all we're doing is a repetition of the two sorts of calculations we've done previously. Either VI times CI equals VF times CF type calculations, or if we're starting from a solid, then to think about the amount that we need and then adding it at an appropriate concentration. So that's it for these videos. In subsequent videos we will think a little bit about both the need to do pHing, how we go about that, and we will think as well about doing serial dilutions if you can't do a nice simple dilution in just one step.